Good afternoon, everyone. Thank you for coming to the IAS lecture here. And it's a great pleasure for me to introduce to you Professor Yannis Phillis from the Technical University of Crete. Professor Phillis was the rector or the president of that university for 12 years. And he received his bachelor's degree from the Technical University of Athens in Greece, and then did his master's and PhD at UCLA. And actually, he met several people, Professor Jacob Huang and also Professor Moshe Zuckerman. They are all from UCLA, so he has a lot of friends here. The world is actually so small.
Yeah.
And
right.
Professor Phillis had faculty position at Boston University in the United States, and he has worked on some really big problems. And today he's going to give us a lecture on national sustainability. As you probably know, this is a huge problem now, right? Climate change, and can we get clean water? Can we get enough food, and etc. So those are really problems for our future. And you remember in the grand challenges of NAE, 14 problems. Many problems are related to sustainability, to our environment. And Professor Phillis is going to give us a lecture on this topic. What he's doing is not just to say with sustainability and etc. those problems, but he's going to show us how to use mathematics to model this. And we'll get into the real sort of mathematics world. And I'm sure we'll benefit a lot from Professor Phillis' lecture. Without further ado, let's welcome Professor Phillis.
Okay, thank you. Thank you, sir. Thank you. Thank you. Okay. Good afternoon, ladies and gentlemen. First, I would like to thank Professors Hong Yan and Jacob Huang for their invitation to be here. Okay, thank you. It's an honor for me to be among you today, and thank you all for coming to this lecture. I also thank Cam, where is she? Miss Cam, there, for taking care of a lot of details of this meeting. It's great. Let me say that from the little I have seen around and from what I've read about your school, I think that you belong to an elite school. It's a great place to be. By the way, just walking here in the corridors and looking at some of your labs, I had an impression I was at UCLA. I've been to many European universities and to many American universities. I had this impression, and I mean it. Also, I noticed something else, that here you have the Institute for Advanced Study, which is something, it has a concept which I love. Its goal is to attract great people in science and technology and do whatever they please in science. This is really important because we have the modern type of scientists and technologists who do things with an eye to applications, to improving the society in a very direct and focused way. And we have science which is grown out of curiosity. And in my opinion, the greatest science in the history of the world has been created out of curiosity. Take the great scientists of the ancient times, of the age of Galileo and Newton, and of course the 20th century. It was mostly because people were curious, and they were curious about the world around us. They were amazed at the miracle we see every day. We get up, and they wanted to explain things, and that's how we see light today. Now let's start with my lecture. The 20th century was a very interesting century, and it's continuing to be as interesting as it can be today, the 21st century. We saw great advances and leaps in science and technology. We learned a lot in physics. We learned a lot in biology. We can do things today like CRISPR-Cas9, for instance, interfere with letters of the DNA, which is just amazing. Such a thing 20 years ago would have been just a dream, nothing more. And we can communicate with any place of the world in just a matter of seconds. Another amazing thing. And you can name a lot of advances. At the same time, though, the 20th century witnessed the two bloodiest wars of history. And it also witnessed destruction of the environment. Now we have entered the sixth greatest extinction era of the planet we live on. And this is not good. And also we have managed to play global games such as climate change. So progress has a price. And the question arises, is our world sustainable? And how sustainable is it? And if it's not, what can we do? What should we do? These are very important questions. And questions that do require answers. I don't have these answers. I just made a few approaches to the truth. I'm trying to investigate the truth with the modest tools I possess, a little math and a little imagination, and I'm going to show you what's going on. So, speaking of, I have this, I forgot. Speaking of climate change, this graph here, let's see. Okay, I have a laser. This graph here shows you the concentration of carbon dioxide in the atmosphere, and you can see that it follows an exponential trajectory. And science is great because science is not just theories. We take measurements, we measure things, and we know almost precisely what is happening around. And this is not good news because you can see here in the late 50s to 60s that the concentration in the atmosphere of carbon dioxide was about 310 parts per million, and today we have gone over 400, and we're still going up. And here you can see what happens to the concentration of carbon dioxide in the atmosphere over the last 400,000 years. Here you have a Dirac delta, which is the present time. And here you can see that we are below the level of 1950. So things are changing, and things are not pleasant. 252 million years ago, our planet experienced a great extinction of species. 96% of marine species and 70% of land vertebrates disappeared. That was a tremendous shock for the planet. And why did this happen? It happened because of ocean hypoxia. That means oxygen just got out of the oceans, out of the waters, and species were dying because of lack of oxygen. Why did this happen? Because in the Siberian traps in the north, there was a tremendous tectonic and volcanic activity which released enormous quantities of carbon dioxide and methane, which caused global warming. Temperature in the tropics went up by about 10 degrees Celsius, which is enormous. Right now, by the way, we have a temperature rise compared to 1900, roughly speaking, of only 1 degree. And you experience here more frequent and more intense typhoons. In Greece, we have many hurricanes. Just a few weeks ago, where I live, we had enormous thunderstorms with mudslides, and lots of disasters. Roads collapsed, bridges collapsed, people were left homeless, and so forth. So it is a changing world, and fast-changing world. Okay, now this happened because of natural causes. Right now, we are substituting for those with our activities, because our activities, our economic activity, causes the release of enormous quantities of carbon dioxide, primarily carbon dioxide, methane and nitrogen oxide, or not nitrogen oxide, nitrous oxide and oxides and some other things, which cause global warming. And we do the same thing that nature did a few million years ago. So things are becoming dangerous, or at least urgent. And so national sustainability is something that we have to discuss, and we have to discuss it in as much detail as we can. All right? Also, national sustainability cannot be focused on, say, the environment only, or the economy only or the society only. It has to view everything globally. So we should incorporate in it the ecological, social, and economic components to see what happens to a nation, to a country. So there are two, first of all, this discussion started becoming part of the agenda, of the scientific agenda, primarily and more systematically in the 1980s. From then on, we began talking about it. And then we said, let's find some models to measure sustainability. So we have two types of models, one called basic and the other one barometers of sustainability. Basic means that we have particular aspects of sustainability, say the economy, or the environment, or whatever else. And barometers of sustainability view things more globally. So examples of the first category is what the Organization of Economic Cooperation and Development has adopted, which is called pressure state response. Take carbon dioxide emissions. You could say that the amount of carbon dioxide we emit every year is pressure. And this is about 36 billion tons annually. Then you have state. You can say that 400 parts per million, this is the state. Response is the level of adoption of renewable energy sources, and this is the response of society to the problem. So this is one type of model. The other one is the ecological footprint. It's very well known. It's the amount of land that a given population demands, requires for its survival, and so forth, and many more. In the second category, we have, for instance, the Environmental Performance Index, which is based on several indicators, primarily environmental. As you can see here, quality, water and sanitation, heavy metals, and so forth. We have the so-called Sustainable Society Index, which has 21 indicators aggregated into 7 main categories: basic needs, personal development, up all the way down to economy, and many more. Another one is the so-called Better Life Index, which has 11 topics: community, education, environment, etc., etc. We have the, this one, by the way, is done, provided interactively on the computer. The user, the reader, looks at each indicator, assigns subjective weights, and then the system gives you an overall index of sustainability. All right, we have also the Human Development Index, which is developed by the United Nations Development Program, and it uses, it is the geometric mean of the scores of 3 dimensions: longevity, access to knowledge, and standard of living, and other approaches, and so on. Now, what I'm going to discuss with you today is the so-called SAFE model, which is a model that my group has created. And SAFE stands for Sustainability Assessment by Fuzzy Evaluation. This model, compared to the previous ones, has several advantages. The previous ones that use many indicators are mostly linear. You take a number of indicators, you assign weights, and you find, say, the geometric mean, or just the mean. Ours is, first of all, nonlinear. We cannot imagine that sustainability is something so straightforward and linear. The model uses fuzzy logic to handle the vagueness of sustainability. If we say that, that a country has good living, a good living standard, what does this mean? How good? How do you measure it? It's fuzzy. And it's also a holistic approach because it incorporates environmental and social aspects. And then at the end, it has a sensitivity analysis module which takes you backwards. And it pinpoints the most sensitive indicators. By the way, we have 69 indicators in this model right now, which might change in the future. And it pinpoints those indicators that have the highest potential of improving sustainability for a given country at a given time. And also, it takes into account past performance. We, if you have a good year and everything is nice and you have very low emissions of carbon dioxide or nitrogen oxides, that does not mean that you are in a good situation, because maybe in the past you were a bad emitter. So you have to include the past performance, exponentially discounted, of course. We use exponential smoothing to bring it to the present. So we account for the past. Also, this model has an additional plus, which is imputation of missing data. We collect the data from national statistics, the United Nations, the World Bank, and many other agencies, authoritative agencies, the Organization for Environmental Economic Cooperation and Development, and so forth. But not all countries provide all data for a number of reasons. So then you have to fill in the missing holes in your model. And we have an imputation, a statistical imputation procedure, whereby we put in the missing data, and then we have a better picture of the whole world. Let's proceed. The model looks like this. It looks complicated, but it's not complicated. First of all, overall sustainability is computed here. Okay? This is the resultant of two components, the ecosystem and the human system. The ecosystem is the resultant of 4 items: air, land, water, and biodiversity. Whereas the human system incorporates policies, economy, health, and education. So we think that with all these dimensions, we have a rather global idea of what is happening in a nation, in a country. And then we use the pressure state response of OECD model just to group each basic indicator. Here we have 69 indicators, as I told you before, and we group them according to pressure state response, and then we go down here, and let's see. We start with basic data, which we collect from authoritative organizations. Then we do exponential smoothing to take into account the past. We cannot, as I told you, work only with a present photograph we took right now. We have to know what's going on for a long time. And then we normalize the data. And why do we normalize the data? We do that because we deal with strange things. We have emissions. We have corruption perceptions. We have a number of immunizations. We have a number of doctors per 1,000 inhabitants. We have GDP. We have percentage of GDP spent for health or education. Those are strange things to each other, right? So we normalize them over 0, 1. 0 means completely unsustainable. 1 means completely sustainable. And then we perform imputation of missing values, as I told you. Then we fuzzify. And here we perform what we call sequential fuzzy reasoning. It goes stage by stage, by stage, by stage, and we reach the final result. And when we finish with the final result, then we go backwards, we perform sensitivity analysis, and then we show some dynamics of what we found. Let's see some more details of that. Here, you can see the indicators we use. Let's go to something like, let's see, health knowledge. No, let's go to health. Okay. Here, you can see that we have the state of health is infant mortality per 1,000 live births per year. Health state, maternal mortality per 100,000 live births per year. These are data we collect. Life expectancy at birth in a society. Undernourishment. And then we have response. Response is how many people you immunize in your country. Immunization for DPT or measles or hepatitis B. Then we have response physicians per 1,000 inhabitants, hospital beds, and current health expenditure, percentage of GDP, access to safe water, access to sanitation, and previously we had some pressure, incidence of tuberculosis, malaria, mortality from particulate matter in the air, which I suppose here you have quite a bit from the mainland, mortality from household air pollution, and so forth. So those are the indicators. We use, as I told you, 69 of those. The number of data we collected were from 1990 to 2016. Roughly speaking, 300,000 numbers. And of course, we have a paper we're finishing right now, we have all the sources of all these numbers so that someone could check them. And then we have, And then we perform, as I told you, exponential smoothing. So we have the numbers of each indicator over a number of years. And we compute levels and trends. A level is where something is, right? A trend is somehow delta level divided by delta time. That is, where does it go? Sometimes we use the level, sometimes we use the trend. For instance, when we speak about forested land, we cannot say that forested land in Ecuador or Peru or Brazil should be the same as in, say, Northern Africa. It cannot be the same. So we look at the trend. Is it improving? Is it deteriorating? There you don't want the level. But when we speak about concentration of carbon dioxide, you need the level. So depending on what we need, we use these two estimates. And here, we have a straightforward algorithm computing the level and the trend. It's called Holt-Winter's algorithm. Any one of you who has taken a course in forecasting or in inventory analysis control might have seen similar algorithms. We adapt this one to the problem in hand, and then we find the numbers, whatever they are, and we normalize them from, as I told you, from 0 to 1. Now look what happens here. Here we have, let's take this one. This one is an indicator that should be as small as it can be. Smaller is better. This one is larger is better, and this is in between. What does smaller is better? Take, again, carbon dioxide emissions. They should be as small as they can be. And we say that from some point and below, they correspond to sustainability 1. At some point and above, they correspond to 0. And in between, we put a straight line. Now, how do we find these limits? How do we find this point and this point? Well, here, for instance, we took the promises of the European Union that were made when the Paris Climate Agreement was signed. So we look at the best performance of an indicator. And we thought that, of course, you cannot have 0 emissions of carbon dioxide. You cannot say that tomorrow morning you'll wake up and you give up fossil fuels and this is it. It's just impossible, right? Okay, but you want to start doing it. You want to start reducing it. To which target? At this point, the European Union target, which is the best worldwide. Tomorrow, maybe a different agreement would be signed, and then you could have a better limit. All right, and what is down here? What is the limit here? The limit here is the minimum of EU 14, the 14 first countries of the European Union. Those are among the most advanced in the world. We took the minimum. We say anything beyond minimum, below minimum is 0. It's completely unsustainable. In other words, we're heading towards something bad. By the way, we've done several simulations. My group has done several simulations of climate dynamics using something like 100 equations. Some of them are differential, some of them are different, some of them are algebraic, and so forth, taking into account certain scenarios of economic growth. And we have found out that even if the Paris Agreement is followed by all countries right now, temperature by the end of this century is going to rise by at least 3 degrees Celsius. The goal, the target of the Paris Agreement is 2 degrees Celsius. So you understand what's going on. We have to have a tighter agreement. That's why I say that we expect things to change, and so the model will change accordingly. By the way, right now, We don't even follow those promises made in Paris. And that's even worse. We're heading to maybe 3.5 degrees. And if with 1 degree we have all these extreme phenomena all over the world, you can possibly imagine what will happen with 3.5 degrees. I don't want to imagine that. I feel really bad whenever I think about it. We have a number of, we've done a lot of simulations, and we have a lot of curves. I'm not going to show them to you now. And they show that things are not good at all. I just looked at some real measurements of carbon dioxide emissions lately in gigatons per year, and they're going up. They leveled a little bit the past 3 years, and now they're going up again. So, and the more we delay drastic action, the more difficult it would be to arrest the system. You see, a system is controllable within some period of time. If you exceed this time, it's no longer controllable. It's like an aircraft that is flying, and something strange happens, the pilot takes over, okay. But if the plane goes down and starts spinning, then there's nothing you can do. It's out of control. So that's the main fear. And that's why many people nowadays, including scientists first and foremost, not politicians, they speak out for climate action as soon as possible. Okay. The other thing is this one. Here we have something that should be as large as possible. Take immunizations. You want as many kids immunized as possible. Of course, the target would be 100%. Okay? So that's how it goes. And then you have something in between, like unemployment. Unemployment cannot and should not be zero. And it cannot and should not be too large either. By the way, in my country, we're experiencing very high unemployment because of the economic crisis, and we suffer a lot. Speaking with several economists from UCLA and other places, here we have all these gentlemen from UCLA, we concluded that an area between 3 and 7% is the best. Anything above 7% is not good, goes down. Everything less than 3% is not good either. So that's what we did here. And here we took again some standards from the EU to signify those points. So that's how we do normalization. And we do it for each indicator separately, of course. Then we do imputation of missing indicators, as I told you. And how do we do that? We group countries according to geo-economic similarities. Okay, in each box, we put countries that have some relationship geographically, but also economically. For instance, Japan is close to South Korea and to China, but we put it in a separate group. Why? Because economically, it's closer to North America than to other countries here in Northeast Asia. Same thing with South Korea. Anything in here has a very high relationship with each other. Boxes connected with a line have a smaller relationship, and boxes that are not connected have zero connection. Okay? So we have these classifications. By the way, the United Nations has adopted something similar, not for imputation, but to show similarities among countries. Okay. Also, you can see here, Yemen belongs to the Arabian Peninsula, but we put it separately because of the civil war. It is a destroyed country. And we thought that it's closer to East Africa than to the Arabian Peninsula. Okay. So we did all that to impute values. And then we devised a simple Euclidean distance measure for each country, first of all, in each box. These are the common indicators between two countries. We take the differences, we square them, sum them, and divide them by the number of countries here. And we choose the country or countries with the smallest distance. Smallest, we set a limit, let's say 0.01. And then what do? We say, for this country, we don't have a number for DPT immunization. Let's take the average of the countries highly related to this one. You might have an objection to this, but we did a test, a nice test. We pretended that the values we knew, we did not know. And then we imputed them. And we found out that the maximum absolute, the mean, absolute error was of the order of 12%. So we knew that we were safe. Therefore, the data we found via imputation were quite reliable, quite good. Okay, then we do fuzzification. Here we have membership functions. Each value we fuzzified. This one, for instance, is very bad with grade of 0.56. With 0.44, and it's also what did I say here? No, it's bad with 0.56 and very bad with 0.44. Okay, so we fuzzify all the values, and so we have a set of fuzzy numbers, nothing else. And we proceed with rule basis. Now, we have proven a theorem that if you use triangular membership functions, and if you use what we call the height method of defuzzification, and if you have some another one or two other conditions, I'm not going to mention them, then your system is monotonic. In other words, if you improve one input, you improve the output. In fuzzy logic with sequential reasoning, it is not guaranteed that if you improve something, we'll get a better result. And so we took special care, mathematical care, so that the model is monotonic. For monotonic rule bases, then, we can assign values to each outcome of a rule, and then play with numbers instead of rules. What kind of rules? Let me show you. You take one input 1, and its value is the fuzzy set 1 with a membership mu 1, and et cetera, et cetera. And an input n has it's a fuzzy set Ln with a membership of mu nj. All right, and then the output is this. This is one rule. If you have a number of fuzzy sets, and you raise that to the number of inputs, you obtain the number of rules you need to form the rule base. Okay, and if you have say 5 fuzzy sets, and you have 6, 7 inputs, then you run into the hundreds of thousands of rules. You cannot do them by hand. So you have to do it algebraically. That's what we did. And one of the requirements for monotonicity is that this output has as membership grade the product of all these mu's here. And if you have the same output for a number of rules, say something is very bad for this rule and that rule and that rule, then the output is the sum of all these outcomes. So it's the sum of the product of those mu's. And again, this is one of the requirements of that theorem I told you. The defuzzification is this simple formula. It's called height defuzzification, invented by Lotfi-Zadeh. I suppose many of you have heard about it. And it's like the center of mass. These are the values of each rule. And these are the values where the corresponding fuzzy set assumes its maximum value. Okay. So you do that, and then you go on with sensitivity analysis. This is a gradient. You take the score, the total score of the safe model, and you perturb it by an epsilon. And you take the difference, you assume that epsilon is 1. In this case, it's 0.01. Okay. And then this is an estimate of the gradient. And then you multiply it by 1 minus xc. What is 1 minus xc? Xc, 1 is the sustainable value, the absolutely sustainable value. 1 minus x is the distance of your indicator from the sustainable value. So you multiply this by the derivative. Why do we do that? Because imagine that you have something that is extremely good, but close to sustainable value. You don't want to improve that. You don't want to tell the governor, put your money to improve this. You want to improve something that is way down from the sustainable value. So we multiply this by 1 minus x, And then you find this number SC, which tells you which is the most urgent indicator to improve sustainability. You could have second order. It's like a second order derivative, a second partial derivative. A second order perturbation, and then this coefficient is this times 1 minus xc times 1 minus xv, the two different indicators you perturb. And then you have the results. And let's see the results. You can see, as expected, that the best countries are Denmark, Sweden, Norway, Switzerland, etc., Iceland, and so on and so forth. And here you can see which are the most influential indicators if you do first order perturbation or if you do second order perturbation. As an example, take I don't know, let's take Denmark. The most important indicator is sea level rise, impact on land. It's a low country. And if you take a second order perturbation, you have sea level rise, impact on land, and immunization against hepatitis. You wouldn't be able to say which indicator is the most important, but now we can. And for each country, we have the second order. You can do third order or any order if the country has enough money to put its money into many sectors. And so we go on with other countries. You can see that the United States is down here, 32nd. Why? Look, its human system is very high, it's 0.8. But its ecosystem is low, it's 0.5. And why is that? Because of too many emissions of greenhouse gases, one thing. Other things too. So you see that here we have renewable electricity generation. It's very low in the United States. And the Gini index. The Gini index is an index of distribution of wealth within a country. A Gini of 0 means absolutely equal distribution. A Gini of 100 means absolutely unequal distribution. In other words, one person takes everything from a country. Of course, you cannot have 0 or 1. In Europe, in the European Union, the Gini index is about 33, 35, something like that. In Sweden, it's about 27, which is the most equitable country worldwide. In Greece, it used to be 30, now it's 35, 36. It's becoming more and more unequal because of the crisis. Here in Hong Kong, does anybody know how much it is? 54. Yes, 54. It's 50. Actually, the latest I saw it was 53.9, which is okay, 54, which is not good. It's quite unequal. Okay. In the U.S., it's 45. Okay. So that's why the USA is quite low. Greece is below the US, and you can see here that we have renewable electricity generation. Greece is a country of a lot of sunshine and a lot of wind, and yet we have very little, relatively speaking, very little percentage of adoption of renewable energy. And also unemployment, of course, because of the economic crisis. All these things popped up because of the model and because of the data we collected. And of course, then you can go down all the way. We have 164 countries, and you can see that the worst ones are Afghanistan, Mauritania, Haiti, the Sudan, Eritrea, and so forth, and you know, with their own problems. One basic problem in these countries is corruption, a lot of corruption. Okay. So the largest improvement we found in SAFE over the period 95 to 2016 was in these African countries, and the strongest declines in these Asian countries. And also, to our surprise, in the beginning we thought we made a mistake. South Korea has a relatively low ranking, but then we realized that this was not a mistake because it has 0 scores, unsustainable, in pesticide use, forest change, incidence of malaria, and freshwater resources. Also, renewable electricity generation is almost 0, not 0. Okay. But then, when we did sensitivity, renewable energy was #1, which means put your money there. and then you will see other improvements. All right. Here we have regions, and you see that European and Central Asian countries and North America are at the top. Here you can see what's happening with the European Union. The first 14 European Union countries are the best, but on top we have Scandinavia. Scandinavia is the best of the best, all right? And here you can see classification of countries according to income. So very low income has very low sustainability, very high income, very high sustainability, which is reasonable, because if you have money, you can have a better education, a better health system, you can take care of your people, you can do things, you can improve your infrastructure and so forth. So this is something that would be expected. And then we compared the results of SAFE with various other systems, United Nations, OECD, and so forth. And we found, what we call here the Kendall's tau is a kind of correlation coefficient, but not the usual statistical correlation. It correlates the order of things, how distant they are, how much they coincide. So it's actually the ratio of the number of indicators that are, as we say, concordant minus discordant divided by all indicators. And that ranges from minus to plus 1, like correlation coefficients. So we see that our model had quite a high correlation with some of these models, but this one, it has a negative correlation. Why? Because this is only environmental. It doesn't view other things. It looks only at the environment. It's narrow, rather narrow. All right. So, and here we have some dynamic aspects. You can see how sustainability evolves over time. This thick line is North America. You can see that there is a slight decline over 1995. Things did not improve. They deteriorated slightly. Latin America and Caribbean improved a little bit. This one is East Asia and Pacific. It deteriorated slightly. And the rest of the regions of the world showed modest improvement. And again, according to income, some dynamics, more or less similar. And here we have correlations of the SAFE score over all the years we examined, every 5 years, of course, because otherwise we'd have had a lot of pictures. And we see that there's a very high correlation of the sustainability SAFE index and gross national income per capita, for reasons I explained to you a few minutes ago. Quite reasonable too. And then we normalized the scores of several regions by taking the score, subtracting the average of all regions, dividing by a standard deviation. And we have this graph here. So you see ecosystem versus human system. In the worst countries of the world are here: low ecosystem, low human system, South Asia, Middle East, and North Africa. The best ones are here: high ecosystem, high human system, Europe, Central Asia, North America, although North America is on the low side. And East Asia and Pacific, very good human system, but there is quite a bit of room for improvement regarding the ecosystem, and so on. And then here we compiled some graphs that show improvement. Europe and Central Asia show a linear improvement from 95 to 2016. Latin America and Caribbean showed a lot of improvement and then slight decline. East Asia and Pacific, we are here, decline, but now things are improving. And Middle East and North Africa decline and now improving, but below the 1995 levels. Okay. Conclusion. Worldwide, we found out via sensitivity analysis that renewable energy generation, corruption, forest change, gross national income, and threatened species are the most prominent indicators. These are the most important worldwide, out of 69 indicators. In developed countries, though, CO2 emissions appear first. And we know that. We all know that, and we know why. Because unfortunately, economic growth goes together with emissions unless we change policies. Okay. Another interesting finding that was that the progress, as I stated previously, towards sustainability in the last 25 years is rather modest. And in North America, we had a slight regression. And this is primarily because of the United States and because of its global warming. The model we devised is a global model. It can easily be modified. We can add and remove indicators according to reality. You know, when we started that some years back, it was quite primitive, I have to admit. We had 75 indicators. In the meantime, we removed several because we didn't have reliable statistics or because countries stopped producing statistics for some indicators. And also, this model aids decision-making, which is not common with other models. By the way, other models can give you decisions. If you have a weighted average and differentiate over an indicator, you get just the weight, which is subjective, and that's it. So it's trivial. Okay? This one is done in a more sophisticated way. And these are my main collaborators, Professors Kouikoglu, this gentleman here, and Grigoroudis, this gentleman here. And that's all, ladies and gentlemen, and thank you for your attention.
Thank you very much, Professor Phillis, for the very interesting talk. And it's, as you can see, a very important problem for the world. Any questions?
It takes the first hand to be raised, and then many follow.
Worse.
One question is, I mean, you show that it's very important, renewable energy
Yes.
is important. Now you have all these models for different all this data for different countries, different
Yes.
criteria, etc. Do you have a way to translate that to money? So you can tell Trump, for example, that it's important to invest in renewable energy money-wise.
Yes.
So if you can have a measure of cost,
Yes.
of sustainability,
Yes.
of the consequences of not having renewable energy. So they can economically compare and say, oh,
yes,
we want to invest in that.
Yes. First of all, let me make a slightly tickling comment. I don't think there's a lot you can tell Mr. Trump. But secondly, we've done some particular studies. We've taken health, for instance, and we've done some optimization and some analysis. We have found even differential equations for biodiversity and health, separate things, completely separate. And we were able to say if the budget of a country is this, if the Ministry of Agriculture or Environment, the EPA, or the Ministry of Education, whatever, gives so much money, where to put it. This is a separate problem. We cannot incorporate money here. Here we can say that if you want to invest in something, invest in this. How much? We couldn't tell. In other words, if we find out that renewable energy is the most important thing, and a country can invest, let's say, 0.5% of its budget, say, put this 0.5 into renewable energy. We cannot do more in this model. But if we go specifically into some areas, as I told you, biodiversity and health, then we have more specific answers, but in a different context, not in this context. And we can tell you, put so much money to hire doctors, for instance, if we talk about health. Put so much money to buy very large and expensive equipment, such as CT scanners or MRI scanners. And put so much to make new hospitals. We've done that. Yeah. But that's a different problem.
So you cannot say what is the cost of so much increase
No, 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 no. Look, if we are talking about climate change, about global warming, yes, we have estimates. Oh, yes, not we. The guy who got the Nobel Prize in economics this year started that, Nordhaus. He has estimates of the cost. They're not precise, by the way. They're very crude, but we do have, and we have several models that followed Nordhaus. We have many, many models that give you estimates. It's in the trillions of dollars.
You can use them
Yeah, he wouldn't hear. He wouldn't listen or hear or anything. The thing is that we have estimates, and we know that the cost runs into the trillions of dollars by the end of the century. So it's enormous. But you know, here is a problem. You estimate the cost, right? Okay, and you do it systematically by using some algebraic and differential equations of economic growth and this and that. But let's say you have some thresholds which you cross. You have a melt in the tundra, and suddenly enormous quantities of methane are released, or you have a stoppage of the thermohaline circulation of the globe. Comes from the Pacific all the way up to the Atlantic, goes all the way to Scotland, comes back, and makes the climate of Scotland mild, right? Okay, and that stops. How can you estimate that? How can you predict that? You cannot predict that. If it happens, then the cost, I would say it's infinite. So those are just, you know, crude estimates, of course. It's very difficult to find out what's going on there. And by the way, anyone who tries to predict what's going to happen in a social or economic system, he'd better take advice from a crystal ball or a magician. The estimates are as good as those. It's only in mechanics, in celestial mechanics, that we have precise estimates of what's going to happen in the future. Otherwise, it's a very risky business. Yes, sir.
Could you say something more about the result about China or India with large population?
Okay. Let me see. Let me go back. Okay, China is down here. It's out of 165 countries, ranks 109th. That does not include Hong Kong, by the way. Yeah, no, it doesn't. It's, you know, here you have a GNI purchasing parity of $65,000 per capita, whereas in China it's much, much, much less. An example. So it's only for mainland China, and the most important indicators here were renewable electricity generation and pesticide use. Let's see where India is. I don't remember that. Let's see. 1 second. India is 129th. Renewable electricity and red list index, species extinction. Those were the most important indicators. We could have third order sensitivity analysis and find 3 or 4. But we said, okay, 2 is enough for the moment. So any other country you would like to see? Pakistan. Okay.
The students are from Pakistan.
Yes. Okay, let's see. I don't know where it is, but Bangladesh, Pakistan. 152, corruption, political rights. So these are the main things. Okay.
Where is Hong Kong?
No, you see, you take the UN data sheet or the World Bank sheet, you don't have Hong Kong. Although Hong Kong has its flag, it has its Olympic team and all that, we don't have data. Also, another thing is the following, that we wouldn't like to examine a, let's call it country or whatever, that has such a small area, because it does depend on neighboring land. It's difficult to start making estimates for such a small place. Yes?
About Singapore, which is
No, 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 no. No, it's the same thing, similar thing. And we don't find data from authoritative sources. Yes?
How about Netherlands in the first?
Netherlands?
Yeah, yeah.
Okay. Wait.
Because the first factor.
Oops.
The first factor affecting it is herbicide. I thought it would be a rising sea level, right?
I'll tell you what's happening. Let me see. Here, Netherlands 7th, pesticide use and renewable electricity. With Netherlands, we assumed that they don't have a problem because they're already below sea level and they have taken measures. And they have a tremendous amount of experience in handling that. They're not going to allow their country to sink. Okay, so have you been to Netherlands? Have you seen those dikes and those? They have the most sophisticated system in the world. So for the moment, that might change 30 years from now. Might. But for the moment, we assume that the Netherlands can take care of its problems in this area. But you're right about that. Whereas Denmark has this problem because whereas Denmark here, because sea level rise, because Denmark doesn't have this experience and doesn't have anything installed. It's just a flat land lying low, but not below sea level. Yeah.
Any other questions? Yes, at the back.
Thanks for the very interesting talk. And just one small question, because you included mainland China. And I wanted to ask, because you included so many countries and all these statistics will matter in your study. And all these statistics were originated from the governments, from their own governments. And you know, from what I heard, that different governments, the way that they gather the statistics may be a little bit different. So take mainland China as an example. If you take the GDP from different sources, they're going to be drastically different. So do you take this into account? Like, are these arrows going to affect your results from to a certain point? Thank you.
Okay, we are aware of this fact. Sometimes, quite often actually, governments want to beautify their data. Let me say that Greece has done that many times, and I know it firsthand, all right? But what we try to do is we try to collect data from certain agencies, the United Nations. I assume that the statisticians of the United Nations do take into account such practices. The World Bank, the World Resources Institute, the what is it called? The Population Reference Bureau, and so forth. We don't go to the official statistics of a government per se. We try to avoid them as much as possible. Okay, and so we have all these agencies. And you know, the data are public. And if we don't find something, then we try to communicate with other groups of people who collect data in this field, again with an eye to this kind of bias. But you're right, absolutely, yes.
Okay, any other questions? If not, let's thank Professor Phillis again for his wonderful
Thank you very
talk.
much. Thank you.
Thank you very
Thank
much.
you.
Thank you. Thank you very much for coming to this talk.